So in our kinematics final practice here, and this number 1, it's saying that balls 1 and 2 are thrown horizontally. So ball 1, ball 2, they're thrown horizontally from the same height h. And they're saying air resistance is negligible, and they're asking about the acceleration and the time it takes to hit the ground. So I made it clear I'm trying to get acceleration and this time. Well, I know the acceleration in this y is a constant as this negative g. And I know they both have to have a change in height of this negative h. They have to start at height h and go down to height of 0. So this delta y, which is equal to 1/2 at squared plus v naught in this y times t. I know the v naught in the y is 0 because the ball is thrown horizontally, so it has no vertical velocity initially. Therefore, my change in height is this negative h equals to 1/2 a, which is my negative g, times t squared. I solve for t, and I get 2h on g. If they have the same height, they get the same time. So that's why we're going to have this acceleration here being equal. And so the selection for ours would be this selection E, giving us equal acceleration and equal time to hit the ground. So then as we continue looking at question number 2, we are given a graph of the height of the ball, and what we're given then is a question here saying, what is the acceleration due to gravity on this planet? So on this graph, I see it starts at a height of 5, and it goes down to a height of 3, and it takes going from 0 to 0.5 seconds. So with that, I know the change in height is negative 2. I know the time it takes is 0.5 seconds, and I know the initial velocity is at rest. And so using this equation, solving for acceleration, where I know this value is 0, I have 2 times the change in height divided by t squared. Change in height is negative 2. T is a positive value. Therefore, I get this 16 meters per second squared. It would be a negative value, and that would be the acceleration due to gravity, which is equal to a negative g. Therefore, our g is 16 meters per second squared. And that would be on our questions here, that would be this option B. As we continue to number 3, for our number 3, what we're given is a graph here saying that this is our position versus time, and it's saying here the average speed between 1 and 2 seconds. What we're trying to find is the average speed in this time interval going between 1 and 2 seconds. So I know average speed is the change in position over the change in time. So if I have 8 meters and 2 meters, then that's what I'm able to get by looking at my graph. I know it's at 8 meters here at the final position, and initial position, it's at 2 meters. If I do then 8 minus 2, that's the change in position, I get 6. Over the change in time is 1, so I get 6 meters per second. As we continue to number 4, number 4 gives us a graph of velocity versus time, and it asks us to try to find the displacement. So I know that displacement is the area of this velocity versus time graph. If I have a positive area here and I have a negative area here, I do 1/2 base times height and 1/2 base times height, and I got a positive 8 meters for the positive area and a negative 8 meters for this bottom area here. Negative and a positive combine to get a displacement of 0 meters. As we continue to number 5, number 5 is giving us 2 separate graphs, a position versus time and a velocity versus time, and it's asking us to describe the car's speed and the acceleration. So we could use the position versus time, saying, well, here this is going with a negative slope to start, going down towards a 0 slope at the end. So it's going from a big negative velocity to a zero velocity. And it looks like that it's slowing down. And it looks like we have here that is slowing down. So we can talk about the acceleration, where I know the slope is the acceleration. So the acceleration of this velocity versus time graph is this slope. And I see that the velocity went from this negative to zero. So a velocity it's having a positive slope, so I have a positive acceleration. But the speed is that magnitude of that velocity, and the speed is getting close to zero, so it's a decreasing speed. So for us, if we have a positive acceleration and a decreasing speed, we need to have positive acceleration and a decreasing speed. So that would be this option C. As we continue on to number 6. Number 6, we're given this experiment here where a ball is released from rest, and this ball here is rolling off, and it has a horizontal velocity. This question here for number 6 specifically relates it back to experiment 1, and what we're trying to find is the speed of this ball in the instant it hits the ground. So if it starts at 1.5 meters above where the ground is, and the ground is at 0, so we have some data here that we can use where we know it starts at 1.5 and it goes down to 0. And we have some data in here that we could try to use, but I'm going to just use that data right here. We know it starts from rest. I know the final velocity is what we're trying to get. I know the acceleration. The acceleration is this negative g. I know the change in this vertical height is a 1.5 because it starts at 1.5, goes to 0. And I know the initial velocity is 0. Therefore, I can solve for the final velocity, set this equal to 2a delta y, square root the velocity, so I square root the 2a delta y. The a is negative g, the delta y is 1.5. Square root that, I get a 5.4 meters per second. So on our selection here, it would be selection D. As we continue then to number 7. On number 7 here, it's asking here, an object's traveling in this straight line across a horizontal surface, and we have this velocity versus time graph that's given to us, and it's asking here, for which method can we determine the total displacement? So what we're trying to find is this displacement. Well, I know the area of a velocity versus time graph is that displacement, so we could get the area of that velocity versus time graph, and in this case it would be 1/2 base times height over that entire time interval, going from that 0 to 5 seconds. Another way we could do this is getting the average velocity. I know if it starts from rest and it goes up to 10 meters per second, that means on average it's going 5 meters per second for that entire time interval. So it could look like so, where on this graph, we're just taking this top triangle and putting it here. And still gives us the same area, gets us to the same displacement. So when we select these two answers, we are finding the area and using our average speed, so both C and D. As we continue to number 8. Number 8, we have a student who wants to try to have an experiment to get this constant acceleration. Well, we know if we drop anything near Earth, we release a ball from rest, we know that near Earth, everything has this constant acceleration of a negative g. So we know this will give a constant acceleration if they devise an experiment by releasing a ball from rest near the Earth's surface. Then they say they're going to put this toy car in a loop such that it travels along different loop sections of a track. Well, we know toy cars in the loop have a velocity that changes. So with this centripetal acceleration, which is v squared on r, if we have a changing velocity, then we know that the acceleration will change. You did your calculations for your cars in the loop. You saw how that velocity changed. So if this velocity changes, then the centripetal acceleration changes, so therefore the acceleration changes, so it cannot be option B. If we have this water-propelled rocket, the rocket has to have this net force to go up. So there has to be a net force on that rocket in order for it to go up. And then if it's going to come back down, then there has to be this net force needed for it to go down. So if we have a net force up and then a net force down, we're having two different net forces which equal to ma. Therefore, we have to have different accelerations. If we have a net force equal to ma and they're both different, then ma has to be different. So therefore, this will not give us a constant acceleration. That would be different accelerations. Lastly, in part D, it says it releases a cart from rest such that it travels down an incline of 40 degrees. That's this angle theta with respect to the ground. So what I did was I drew in the cart and the track here at that angle, and I tried to draw onto here so that way I could get to my free body diagram, getting the sum of the forces equal to ma. I have this mg sine theta minus this force of friction, mg sine theta because it's this angle opposite, rather the mg is opposite the angle theta, so it's mg sine theta minus this force of friction equals to ma. I know mg sine theta minus the normal force times this mu, that is the force of friction, equals ma. So mg sine theta is going to equal to, or mg sine theta minus mg cosine theta, that's the normal force, which normal force equals to the mg cosine theta, times mu equals ma. If I divide by m on both sides, I have a is g sine theta minus mu g cosine theta. G doesn't change, theta doesn't change. This coefficient of friction is a constant, therefore a is also a constant. So as we look at this, then if we have this as a constant acceleration, then we will also get a laboratory experiment showing that. As I continue to number 9, number 9 is trying to get us to get a displacement. A displacement calculation from acceleration versus time graph. We know that we have this acceleration for 3 seconds and then a negative acceleration for another 3 seconds. We assume that the car starts from rest, and what we're trying to get is that displacement for the entire time. So I know the acceleration is 4 meters per second squared going in between this time interval of 0 to 3 seconds. The acceleration between 3 and 6 seconds is -2. We know it starts from rest at time equal to 0. So going from time equal to 0 to 3 seconds, I can use my 1/2 at squared plus v naught times t. V naught is 0, so a is 4, t is 3. I get the displacement of 18 meters in that first 3 seconds. So I call this x1. Going from 3 to 6 seconds, now the initial velocity at 3 seconds is going to be different than rest because it's been accelerating, it's now moving. So I'm going to solve using v equals a times t. I know the acceleration for the first 3 seconds was 4. The time was 3 seconds, so it was initially going 12 meters per second at 3 seconds. Then we have a negative acceleration. So I'm going to use my 1/2 at squared plus v naught times t. I'm going to use this 3 seconds in here for the t because we're doing 6 seconds minus 3 seconds, which is our time, which is 3. So 1/2 times the a times t squared plus that 12 meters per second because that's how fast it was going at 3 seconds times 3 seconds. Now I have this delta x of 2 to be 27 meters. 27 meters plus the 18 meters, I get 45 meters. So now we have number 9. As I continue, as I get to number 10. So on number 10, we are given now that we have an object attached to a string moving in a circle at a constant speed. And they're saying which of the following is correct. Well, I know as we go in a circle that the velocity changes. If I have a radius r, I have a velocity down, then a velocity to the left, a velocity up, and a velocity to the right. So the velocity is changing. Therefore, there is an acceleration here. So I know the centripetal acceleration is v squared on r. As I look at question part B, it says in here that the object's velocity is the same as its speed. Velocity is not speed. I also know then it says for letter C, the object does not require force to keep its state of circular motion. Well, if there's no force, no centripetal force, then there's no circular motion. And then that says to cut the string. Well, if there's no string, then there's also no centripetal force. And we also know that this velocity is tangential. It doesn't go radial. So when we say radial, if we were to release it here, the velocity would not just all of a sudden fly out this way. If we release it at that point, the velocity is tangential, not radial.